And also, thank you for having me here in this wonderful place. I'm very happy about giving the talk. Let me first say, so on Monday I realized that I will be the only person giving a Blackboard talk and that all people have to move to a different room just for this talk, and I thought it was not correct. So I worked out some slides and yeah, sorry for this mess. So now it's fine, I think. Yeah. Okay, so this will be a talk on deformation quantization. So we will hear some new things, but also some things that have been in previous talks. So I just hope that I'm not boring you too much. And anyway, so let's start to motivate a little bit of what I'm doing. And actually, the first slide is very similar to something that Baal told us in his talk. It's almost the same slide, I would say. And okay, so what do I want to do? I want to find a star product on a smooth manifold M by doing the following. First of all, I want to find a symmetry G on M, and I will tell you what this symmetry is later. Second step is I want to quantize that symmetry, which or the Hopf algebra corresponding to this symmetry. And in a third and last step, I want to get a star product on the manifold and also a non-commutative Cartan calculus using this quantization of the Hopf algebra. Okay, so it seems a little bit weird that first you are taking a step back somehow for finding this symmetry, quantize this, and then do the actual thing that you want to do, but I will show you that this is actually a good thing and could be really helpful in many cases. And this recipe is known as Drinfel'd deformation quantization. Okay, schedule. So first of all, I have to tell you in more than just one slide what Drinfel'd deformation quantization is. And I guess for some of the people here in the audience, this will be quite boring because, yeah, you know pretty well. But I, anyway, yeah, want to tell you what it is, and also tell you that it's actually very beautiful, very natural, and it's useful. It's a very useful tool. And then in the second part of the talk, I will do the contrary part, like telling you that it's actually bad in several cases, that it's not useful for several manifolds. Yeah? And so in the second part, I will tell you that for the symplectic Riemann surfaces, you cannot have a Drinfel'd star product only on the torus. And so this is based on a paper that I wrote with Pia, Chiara, and Stefan. And yeah, I will tell you that for these Riemann surfaces, one should look for something else. And in the last part of the talk, I want to give one more class of, let's say, non-twist star products by the use of Morita equivalence. And so in a nutshell, what is happening here is I will show that the Morita equivalence classes of Drinfel'd star products and symplectic manifolds are trivial. Yeah? And this will give us a tool for telling if a star product is twist or not. And this is also based on a paper with my supervisor who's sitting there. And okay, so that's the schedule. Hopefully we can make it. Okay, so I will start with telling you what Drinfel'd deformation quantization is. I will work over the field of real or complex numbers. And first of all, what is deformation quantization? So as you know, it's natural to look at Poisson manifolds in the case of star products. And so if I take a Poisson manifold, then I say that a star product on this Poisson manifold is a bilinear product on the formal power series of smooth function of this manifold. and it's actually given by a formal power series of bi-differential operators, bk here. And okay, there are some properties. You would like to have the pointwise product of functions in zero order, and you want to have the Poisson bracket back in the first order. And I mean, what you are mimicking here, so with this, it's just a correspondence principle, which tells you that the semi-classical limit of the star commutator gives you back the Poisson bracket. Oh, I'm sorry. Okay. And then what you also like is that you have the same unit as the algebra of functions of the pointwise product, which basically means that bk1 is 0 for all k greater than 0. Okay, and then this algebra of smooth functions with this product star is called deformation quantization of our Poisson manifold. And I want to stress that this is really for a fixed Poisson bracket here. So it's really this is part of the data, and later on this will be crucial. Yeah? That we are not only looking at the manifold but also at the Poisson bracket. Okay, then symmetry. What is a symmetry of a smooth manifold? I would say that it's if you have a Lie algebra G, such that there's a Lie algebra map into the smooth vector fields of the manifold, which basically means, in other words, that you have a UG module algebra action on the smooth functions. So UG in this case is a Hopf algebra with the usual co-product and co-unit, also antipode that you all know, so I think I don't have to write it down. And module algebra action, okay, maybe I'll write down something. Module algebra action in this case means that you not only have a left action, but you also know that, for example, if you act with psi on the pointwise product of two functions, then you know that this respects this product. So you get psi1, psi2, where this is just Sweedler notation of the co-product. And if you act on the unit function, you will get the co-unit of your element, sorry. Okay. Then, so this is like the first step, right? So we know now what a symmetry of our manifold is. Then the next step is quantize it. So how to quantize? And the tool, like it's written on the top here, will be a Drinfel'd twist. And I tell you what a Drinfel'd twist is. It's an element of the second tensor power of the universal enveloping algebra of your Lie algebra formal power series with some properties. And the properties are the following. First of all, it's a two-co cycle, which means that you have this property. Second, it's normalized. So if you act with the co-unit on the first or on the second leg, you will get 1. And it also starts with the one tensor 1. And later on, I can tell you what the actual reason for these axioms are. The reasons are. Okay, that's a Drinfel'd twist, and we have seen several of them in the talks. Also later on, I will show you one of them. Okay, so I want to tell you why this is useful. So what can we do with a Drinfel'd twist? So let's just take any twist. Then you can twist the Hopf algebra, so the universal enveloping algebra, in the following way. So as an algebra, you simply take the h-bar linear extension of your universal enveloping algebra, but you twist the co-product and also the anti-product. You keep the same co-unit, and this looks like the following. So the co-product is twisted in this way, and the antipode like this, where beta is this element. F1 is the first leg of the twist, F2 is the second leg. Okay, I think all of you have seen this before. Okay, and typically, so if F is not that trivial, the UGF is non-commutative. So we could say that we quantized our symmetry. So this is like the second step of our recipe. So let's look to the third and last one. So we actually want to quantize our manifold, or the functions on our manifold. And this is how it works. We need a symmetry and a twist on this symmetry G. And then we can write down a product star F on the formal power series of the smooth functions. And the formula is given here. So again, F1 is the first leg of the twist, and F2 the second one, and -1 means that I'm looking at the inverse twist. And if I act with the first leg on F and with the second leg on G, and I multiply afterwards, I can prove that this really gives a product on this space. And one can prove that this is actually really a star product. And okay, this is what Drinfel'd twist deformation quantization is about. So the definition here that I want to state is what is a twist star product. So I fix now a star product star on a Poisson manifold, and I call it twist star product. If I can find a symmetry G on the manifold and a twist, such that I can write this star product as the twisted pointwise product using this twist. Okay, and so here I state one case where this is happening, and this is like something we've seen now a lot of times during this conference, and this is the Moyal-Weyl product on let's say R2, and if I choose coordinates x and y and a standard Poisson bracket, then as we know, the Moyal-Weyl product looks like this here. So M just means multiply the first and second tensor component. And this is actually a twist star product if we use the following twist here. So the minus sign is just needed because I'm acting with F -1, which is in this case then just plus here. And the symmetry is TR2 or just R2 with the 0 Lie bracket, and I act with the Lie derivative. Okay, so this means that this is not empty, there are twist star products, right? And then you can actually do more. If you have this twist and a twist star product, you can also twist the Grassmann algebra of differential forms, and this looks like this with very similar formulas. You simply act on the first form and then on the second one, and then you wedge afterwards. You can prove that this is a bi-module for the twisted functions, which is equivariant with respect to the twisted symmetry, so everything like works perfectly. And the twisted module action is also very easy. Simply act with the first leg of the twist on the first thing, with the second leg on the second thing. So it's very natural, very easy. And you can do many more things, but I don't have time for all of this. I will just say, yes, there's even something like a twisted Cartan calculus, and for this kind of thing, you should look at the work of those people here. And it's very, very good. But let me just go back for a second and to the definition here. So the question was now, are all star products actually twists? So can I always find a twist such that this formula holds, yeah? And one would say no, so this would be weird, like there should be more star products than twist star products, but actually proving this is not so easy, because what you have to do is you really have to check that for all symmetries of your manifold, so if you fix a star product, yeah, right, then you have to prove that for all symmetries of your manifold, you can not find any twist on these Lie algebras such that this formula holds. So you have to check a lot of things, yeah, and maybe you will never finish. So, and so it was not really clear how to prove this, even if it should be true that there are like star products which are not twist. And yeah, what I'm telling you is actually we could do it, and the thing is that twist star products are, so this is not working well with many symplectic manifolds. And so in the rest of the talk, I still have some time, I want to tell you in which cases this is not working. I cannot find a twist star product. Okay, so let's start with the second part. Yeah, we fix a star product in a Poisson manifold. What we can prove is the first order of a twist, so if we denote this by R prime, one can prove that this is actually a classical R matrix, which means that the classical Yang-Baxter equation of this R equals 0 will be needed later. What you can also prove, what is very useful, is that actually if your subproduct here is a twist subproduct, yeah, for this twist, then what you know is that the Poisson bracket is actually just the R matrix, so this object here, acting on the functions and multiplying them. Yeah, so this is what is happening here. So it's a, let's say, very simple form of this Poisson bracket. Yeah? And using this, what we proved is, like, if you have a symplectic compact connected manifold with a twist subproduct on it, then we know that there's a transitive action on this manifold, so that it is a homogeneous space. And yeah, so this is like the first step. And using this, one can see that you cannot have any twist subproduct on the symplectic Riemann surfaces of genus greater than 1. I will tell you how this works. And with a little bit more work, you can also see that there is no twist subproduct on the symplectic 2 sphere. Okay, so let's look. So just at the sketch of the proof, I will go very fast. Okay, so for the first one, as you all know, that the Riemann surfaces are compact connected, but not homogeneous for genus greater than 1. And so using the lemma, the part 3, yeah, we just see that in this case we cannot have a twist subproduct on these spaces. So these are these higher pretzel surfaces. You all know them. Okay, for the second part, as I told you, it's a little bit more complicated because you cannot simply use the lemma. But what you know is, yeah, also part of the lemma was that the first order of the twist is a classical R matrix. So, and you can also, by just doing some quotient, you can say that this is actually a full rank. Yeah? Everything stays the same. And then there's a very old paper here that tells you how all transitive Lie group actions on S2 look like, yeah? And that this is done by, so this can only be by semi-simple Lie groups, and using this, you can prove that there are no twist subproducts on the sphere because you know that there are no non-degenerate R matrices on simple Lie algebras just by Whitehead's lemma. Yeah? And this is how you prove it for the two-sphere. Okay, the last part. Yes. So here we start with a smooth complex line bundle L over M, and what we know is that the smooth sections, they are a Morita equivalence bimodule for the functions, which means that it's a finitely generated projective bimodule with an algebra iso of this form. Yeah, so this means these are the right linear endomorphisms, so right linear for the functions. I mean, it doesn't matter because here left and right linear is the same thing, but okay. And yeah, so this means Morita equivalence bimodule. I mean, Gianni also told us about this. Yeah. And yeah, so there's a paper by Bernstein and Waldman, and they proved something very similar for star products. Yeah, and they said if you have a star product and a symplectic manifold, and you take a smooth complex line bundle, what you know is that you can find a second star product, star prime, on the same manifold and also with the same Poisson bracket. So this is really what you need, such that you can find an iso of star product algebras, yeah, of this form. And okay, well, what you see here, so this is really the star product that we started with. This is the new one, and this here is like a deformed module action, yeah, of the functions on the sections. And I mean, this is done by using some Fedosov-like proof. Yeah. And yeah, okay. And what I also prove, what is pretty nice, is that star and star prime are equivalent as star products if and only if the first Chern class of the line bundle is 0. Okay, yes, this is the theorem again, and now we can just say that star and star prime, so just any two star products on a symplectic manifold, are Morita equivalent if there's a line bundle and an iso of this form. And what you can prove is that this really gives back the usual Morita equivalence of star product algebra. So this is the correct notion, let's say, of Morita equivalence in the case of star products. So this is good. So how can we use this for twist star products now? And yeah, so I simply state the theorem. What we proved is, so if we start with a symplectic manifold, and we also have a transitive G action on this manifold of a Lie group G, then mutually exclusive R, that we have a G equivariant line bundle with non-trivial Chern class over our manifold M, and that there is a twist star product on our manifold corresponding to this Poisson bracket based on UG, yeah, where G is now the Lie algebra corresponding to our Lie group. Okay, and what you get from this is that you cannot have any twist star product on the symplectic CPN -1 based on U, GL, and C for any sub-phi algebra. And so this includes also the Barrison triplets star products from Martin Schlickenmeier, which is a huge class of star products. And they are not twist. Okay, and so proving the last point is very easy. You have the tautological line bundle CPN -1, which has non-trivial Chern class, and it's GL and C equivariant. So this just means if we use this here, you can see there's no twist star product on CPN -1. okay, since I was very fast, I can even show you parts of the proof. And okay, so let's say if that both of these hold at the same time, yeah, 1 and 2 both hold, then what you know is, so for a line bundle being G equivariant, this only means that the smooth sections are UG equivariant. And if you now also have a twist on the universal enveloping, you can twist the bimodule of sections in the following way. Yeah, so this is also what I showed you before. So you just take the usual let's say here left module action. Yeah, so with functions on sections, and you act with the first leg on the first, with the second leg on the second, and you can see this is a bi-module for the twisted functions, and it's UGF equivariant, so equivariant for the twisted symmetry. But you also know, okay, so first of all, this means since you can see that this is in zero order of H bar, that was just F times S, you can see that this actually gives you an ISO of C on the power series algebras, where now this here is simply the bi-module action, so the twisted one. And you also know from the theorem of Waldmann that since you have a line bundle, yeah, then you can now look at the Morita equivalence class of your twist subproduct using this line bundle. And this means in the end that you have an ISO of the twisted functions for with the subproduct corresponding to the line bundle, yeah, and this means that the first Jam class has to be 0, which is not possible since we said it's non-zero. Yeah, so we cannot have 1 and 2 at the same time. It's not possible. So there are some open questions, and I will state the first two here first. And yeah, so this means can I have more of these? So are there more ways of showing it on a symplectic manifold? There are no twist subproducts, and can I even say something about the truly Poisson case? Yeah, because okay, this was not even touched yet. And I mean, in the end, what I'm aiming for is to classify twist subproducts. Yeah, so it would be nice to, I don't know, maybe having a list of, I can say these are all the twist subproducts, and that people can see. Okay, in this case, I can use it. I have all the nice properties of twist subproducts, and if I want to work in a different setting, I cannot use it.